All right, so calculating that solute potential, there is a second equation. And that second equation, so we're going to calculate this, is negative ICRT. I'm going to tell you what these things are. Where, right, and I is the ionization constant. And for this, for sucrose, it's 1. So remember when sucrose dissolves in water, the water surrounds it and forms a hydration shell and so on, but the sucrose itself does not break down per se. It's not an ionic compound. So for sucrose and most of the things that we would use in this class, the ionization constant would be 1. Well, let me relate that back to an ionic compound like salt. Salt is sodium chloride. And what happens to sodium chloride when it goes into water? It splits down into the separate ions, right? Sodium and chloride ions. And so for that compound, it breaks down into 2 particles, and so it would have an ionization constant of 2 because it breaks into 2 separate things, all right? So sucrose, that doesn't happen, and so it's an ionization constant of 1 for sucrose solutions. Then C, we talked about C yesterday. What do you suppose it means? Concentration, it's the molar concentration. Of the solution. And a molar concentration, like when you have a 1 molar solution of sucrose, what that means is it's moles per liter. That's the units kind of that. So 1 molar has 1 mole per liter, 2 molar has 2 moles, and so on. All right, so then let's look at R. R is another constant. It's called the pressure constant. So this will be for anything exposed to the atmosphere. It's exposed, it's just an atmospheric pressure. The pressure will be the same for everything. And so that is 0.0831. And then it's liter, bars, per mole, Kelvin. Those are the units on that. And then lastly, T. What do you think T stands for? Temperature. And in this equation, so that things cancel out, the temperature is in Kelvin. If you remember from chemistry, to get Kelvin, you take the degrees Celsius and add what to it? 273. All right, so that's what everything is. So notice these two, let me get a different color here. This is a constant, and this is a constant. So these 2 things, especially if we're using sucrose, are constant. So therefore, to figure out the solute potential of a solution, you need the molar concentration and the temperature of the solution. And if you can do that, then you can, if you know those 2 pieces of information, you can plug them into this and figure out the solute potential of the solution. So let me give you a practice problem. All right, so what is the solute potential of a 0.15 molar solution of sucrose? At atmospheric pressure, that means that the pressure is just going to be that 0.0831. There's no additional pressure at 25 degrees Celsius. So what I'd like you to do is use this equation and see, write it out with the units. I'd like you to try and show your work with that equation. Put I, put C, put R, T, but put the units on there and cancel out the units and see if you can figure out what's the unit that the solute potential is measured in. Yes, for I we're using 1 because we're talking about a sucrose solution. So water potential and figuring out solute potential, these are 2 other equations on the AP Bio equation sheet. Okay. And on the AP Bio equation sheet, you're given like the 0.0831, like what those are, so you don't have to memorize those. Okay, you guys, so as asking the solute potential, so let's do this NiCRT. Let's just plug this in. This right here is your C, 0.15, and this is your T. And so when we, solute potential, when we figure this out, we have a negative, and then it's a sucrose solution, so the ionization constant is 1. And then your C is 0.15 molar solution. The units on that is moles per liter, so it's going to be, to make it cancel out correctly, you need to use the units here, so 0.15 moles per liter. And then R is our pressure constant, so it's 0.0831 liter bars per mole Kelvin. And then lastly, our temperature was 25 degrees Celsius, but it's in Kelvin, so we add 273 to that, so you should have 298. Okay. All right, so that's your setup. And so then when we cancel out our units, the Kelvin cancels out, liter cancels out, moles cancel out, and you end up with bars as your unit. All right, so then you multiply that all out. Did you guys get a negative 3.7 bars? All right, and that would be your solute potential. So then, let's say it says of a solution at atmospheric pressure. So let's say this is the solution here, and so we just figured out that that solution has a solute potential of negative 3.7 bars. What would be the water potential of this solution? figure that out? You should be able to. This solution, what do you need to know for to figure out the water potential? Solute potential and the pressure potential. What do we know about the pressure of the solution?
0.
It's 0 because it's exposed to the atmosphere, and so therefore the pressure is 0. So in this case, the water potential is equal to the solute potential, okay? And so this is the thing that the last little piece of information that you needed to know to do pass number 2 on the water potentials problems. All right, so questions 3 through 7, you use this equation in some manner to figure out. All right, so they'll give you enough information to work with that. So that's what you need to look at. And so if you look at number 3, we're running out of time here, aren't we? We only have a couple minutes. I was hoping we'd have enough time to do number 3 together, but so try 3, 7. You should have made 1 and 2. All right. What's the 1? Alright, so use this, finish up those through number 7 for tomorrow. Tomorrow we'll get your data from your lab. And we're going to finish up, there's the last little bit of the notes I think we have to still take in this class. Alright. I think it's not very much. No, it's not, maybe only like 5 minutes or so. But.